Hi everyone, we're going to do chapters 16 and 17. Instead of having class this week, I have recorded this video that covers both chapters. Chapter 16 is inferences about population means, and chapter 17 is two-sample problems. I do not want this video to take an hour and a half, as I'm sure you don't either, so we're going to get through it in a very efficient way here. First thing we need to talk about are conditions in order to do this. Of course, as always, we have to have an SRS. That's very important. We also need to have normal distribution of the observations. Previously, we had to know what sigma was, but in real life, sigma is unknown. We don't really know what sigma is, and so we're going to learn in this chapter how to avoid needing to know sigma. And note here that sigma is an unknown parameter, as is mu, and mu always is. So now we're going to learn how to deal with an unknown sigma. A definition I want to introduce you to is standard error. The standard error is the sample standard deviation divided by the square root of n. So it's s divided by square root of n. Okay, that's the standard error of the sample mean x bar. Okay, standard error of x bar. So let's become familiar with something brand new, the t distribution. So we've been spending a lot of time this semester with z, and now we're going to learn about t. T is an alternative to z. You would never use them both at the same time. T kind of replaces z when you don't know sigma. And so that's the key here. If we knew the value of sigma, we would base our confidence intervals and tests for mu on the z statistic, which we have we covered in the last quiz. The z statistic has standard deviation, has standard normal distribution, in 0, 1, but in practice we don't know sigma, so we can substitute the standard error for the standard deviation. That's the key substitution there. So we're substituting standard error for standard deviation. The statistic that results does not have a normal distribution. It has a new kind of distribution called a t distribution. So the key here is that once we substitute in the standard error, our data is no longer normally distributed. It's distributed with a t distribution. And there's more than one of them based on how large the sample size is, which we'll talk about in just a second. So if we draw an SRS of size n from a large population that has normal distribution with mean mu and standard deviation sigma, the one sample t statistic is given here. So notice the very, very similar structure to the z statistic. The z statistic was x bar minus mu over sigma divided by square root of n, that adjusted sigma that we've seen before. But here, since we've substituted in the standard error, we have s divided by the square root of n in that denominator. And again, we'll have n minus 1 degrees of freedom. When we're looking at this degrees of freedom, this is going to become a lot more important with the t distribution. So, t versus z. This chart here, this graph, shows us the standard normal curve in the solid line, which, if you notice here, is it's taller. See, it comes up the tallest, and it also shrinks down, and it's the flattest down here at the end, like this. It goes down at the sharpest angle and collapses to the bottom quicker. We have t with 2 degrees of freedom in the big dash, and then in the tiny dash we have t with 9 degrees of freedom. So degrees of freedom is n minus 1. It's the number of data points minus 1. So what this shows us is, with the smaller number of data points, when n is smaller, what happens to the t distribution? The t distribution becomes flatter. Notice here it doesn't actually ever reach the bottom here. It's not nearly as close. So that shows you that the area under this tail, right in here, is going to be larger than for the normal curve. And also, it's flatter. It does not get up as high as the standard normal curve does with 2 degrees of freedom. With 9 degrees of freedom, it's getting closer. Notice how it's kind of approaching the normal curve the more data points that you get. And in fact, when you approximate the t-distribution with, say, 1,000 data points, something very, very large, then it becomes the normal curve because the number of data points is so high that the t-distribution ends up behaving exactly like a normal distribution would. So ultimately here I want you to note that t is flatter and wider than is the normal curve. So of course we have confidence intervals. Draw an SRS of size n from a large population having unknown mean mu. A level C confidence interval for mu is x bar plus or minus the critical t value times s over square root of n. So notice here what this is saying. It's saying that our estimate for mu, which is of course x bar, it is our estimate for mu plus or minus this margin of error. And the margin of error is the critical t value times the standard error of the data. Okay, s divided by square root of n is that standard error, not a standard deviation anymore. So the t star is the critical value for the t, and then in parentheses n minus 1 density curve. And that sounds a lot scarier than it is. It's just a density curve. This is a density curve, right? These density curves, we've been hearing about them. Proportion curves, whatever you want to call it, they all mean the same thing. So that's a density curve. T of n minus 1. The n minus 1 is again the degrees of freedom. So if we have 10 data points, then we would be looking at the t parentheses 9 density curve, and that 9 is 10 minus 1. It's the n minus 1. A one-sample t-test is also very, very similar to what we've seen before, where we are taking the null hypothesis of mu naught. We're going to have a t-test of x bar minus mu naught, where again the mu naught is the mu of h naught, and then in the denominator is the same standard error that we have seen. But instead of having a sigma, we have an s, because we're no longer dealing with the population standard deviation because we don't know it, so we can't use it. So instead we're dealing with our sample standard deviation. So let's go back to the sweetness loss example that I had included in the chapter 13 and 14 PowerPoint. Since the standard deviation for the population, sigma, is rarely ever actually known, here is a more realistic analysis of the cola sweetness example from chapter 13. This is more realistic because we're not relying on the fact that we know or don't know sigma. Okay, so cola makers test new recipes for loss of sweetness during storage. Trained testers rate the sweetness before and after storage. So before and after. Ideally, what would the difference be between before and after? Ideally, the difference would be no difference, right? We don't want the cola to be any less sweet after it's been stored. That would be bad for business. So the ideal situation would be that the before storage sweetness and the after storage sweetness are both the same, or in other words, the difference is 0. Okay? So here are the 10 tasters. So we have n of 10 tasters, and here are the differences in the cola's sweetness. Are these data good evidence that the cola lost sweetness? So let's plan our solution. Tasters vary in their perception of sweetness loss. So we ask the question in terms of the mean loss, the loss, mu, for a large population of testers. The null hypothesis is no loss, and the alternative hypothesis is to say that there is a loss. So if there is a loss, then the mean loss is greater than 0. Does that make sense? So if the mean loss, that's mu right here, if the mean loss is 0, that's to say that there's no loss. And if the mean loss is greater than 0, then some loss has occurred, or in other words, there is a loss. So let's solve this. First, check the conditions for an inference. We need to regard these as an SRS. We got to make sure we have an SRS, and we can't judge normality from just 10 observations. There are no outliers, but the data are somewhat skewed. Skewed is when it's not exactly that nice, normal curve. It might be a little off to one side or something like that. That means skewed. That is what skewed means. So because of this, we don't know normality exactly. P-values for the t-test may only be approximately accurate. The basic statistics are, when we just calculate this from the data that we got from these 10 tasters, the x-bar is 1.02 and s is 1.196. Again, this is the mean and the standard deviation for these 10 data points. And so we can test a one-sample t-statistic here. If we just plug in the x-bar, and of course the mu naught is 0, that would be the mu of h naught. And again, we just pulled that from right here. The mu of h naught is 0. So we just plug in 1.02 and 0, and then in the denominator s and 10 for n. And we run this through a calculator and we get a t-value of 2.697. So here's what this looks like. Here's our t-distribution with 9 degrees of freedom, and this t-value puts us at 2.697, okay, which means that the p-value here is 0.0123. It's the area of this little tiny tail is 0.0123. So if we have found that, and the way that we found that is we can also look at this right here. This is just calculated by subtracting, but if we look at this here, looking at from table C in the back of the book, degrees of freedom 9, so that means that 2.697 puts us in between these two t values, these critical t values, puts us at a one-sided p of 0.02 to 0.01, somewhere in between there. Okay, and so if that is the case, which we are seeing here with a 0.0123, if that's the case and we compare that to an alpha value of 95%, so alpha would be 0.05, it doesn't really matter if we only calculate it to 2 decimal places or to 4 decimal places, because either of those, 0.02 and 0.01, are both lower than alpha. So the p is lower than alpha, and so we reject the null hypothesis. And again, the null hypothesis was a mu of 0. If we reject this, we accept the alternative, which means that there is a loss. And so, in other words, there is quite strong evidence for a loss of sweetness. Another version of T procedures is what's called a matched pairs. And in matched pairs, we compare the responses of 2 treatments in a matched pairs design. Find the difference between the responses in each pair, and then apply the one-sample T procedures to the differences. And so when I say difference, I mean you're subtracting one treatment piece of data from another, and then the difference becomes your real data points. We're not going to go into a lot of this right now because it's fairly involved, and before we do any of those, I want to make sure we have it in class. So just to recap how we use T procedures, we must have SRS, and normal is preferred, except in the case of small samples. We don't necessarily know that it's normal. Normality has to require a certain amount of data before it's even possible to be normal. With samples less than 15, size 15, we use the T procedures if the data appear close to normal. If the data are clearly skewed, do not use T. Also, do not use T if outliers are present. With a sample size of at least 15, the T procedures can be used except in the presence of outliers or skewness. Okay? And within large samples, the T procedures can even be used for skewed distributions. when n is greater than or equal to 40. And that is also that is somewhat variable between textbooks, but for this textbook we'll say it's 40. Now we're going to shift the gear into two sample problems, and in two sample problems we're going to be comparing two populations or two treatments, and this is one of the most common situations encountered in statistics. So we want to make sure that we set our goal correctly. The goal of inference is to compare the responses to two treatments or to compare the characteristics of two populations. And we have a separate sample from each treatment or each population. But unlike the matched pairs design that we looked at just a second ago, there's no matching of the individuals in the two samples, and the two samples can be of different sizes. Inference procedures for two sample data differ from those of matched pairs. Here are some examples of typical two sample problems. Example 1, physical therapy. Does regular physical therapy help lower back pain? A randomized experiment assigned patients with lower back pain to two groups. 142 received an examination and advice from a physical therapist. Another 144 received regular physical therapy for up to 5 weeks. After a year, the change in their level of disability, ranging from 0 to 100%, was assessed by a doctor who did not know which treatment each patient had received. So this is going to be an example of a matched pairs design because, this is a two-sample problem. I had confused my notes. Another example of a two-sample problem is when a psychologist develops a test that measures social insight. He compares the social insight of female college students with that of male college students by giving the test to a sample of female students and a separate sample of male students. This is also an example of a two-sample problem because they are independent they may not have the same sample size. And in fact, in example 1 here, they don't have the same sample size. Okay, what about this one? Looking back on love. Choose 40 choose 40 romantically attached couples in their mid-20s. Interview the man and woman separately about a romantic attachment they had at age 15 or 16 and compare the attitudes of the men and women. This is a matched pairs design because the attitudes of husbands and wives may be connected, so we must keep them together. Example 2, whom do you trust? Companies often place advertisements to improve the image of their brand rather than to promote specific products. In a randomized comparative experiment, business students read ads that cited either the Wall Street Journal or National Enquirer for important facts about a fictitious company. The students rated the trustworthiness of the advertisement on a 7-point scale. Compare the mean score for the two types of advertisements. This involves two independent samples, so we would do a two-sample problem. Those students who read the Wall Street Journal and those who read the National Enquirer. Okay, so we would do two-sample for this. Number 3, chemical analysis. To check a new analytical method, a chemist obtains a reference specimen of known concentration from the NIST. She makes 20 measurements of the concentration of this specimen with the new method and checks for bias by comparing the mean result with the known concentration. This involves a single sample, so it is neither a two-sample or matched pairs. Okay? So for a single sample, let me just clarify a little bit further. A single sample with 20 measurements, that would count as a one sample T. Okay, one sample T that we just learned about earlier. Excuse me. So here are some conditions for inference comparing two means. Say we have two SRSs from two distinct populations. The samples are independent. That is, one sample has no influence on the other. Matching violates independence. So we need to measure the same response variable for both samples. So matching, when I think about matching, I think back about on the dependent probability and or conditional, where one influences the next. The other condition is that both populations are normally distributed. The means and standard deviations of the populations are unknown. But in practice, it is enough that the distributions have similar shapes and that the data have no strong outliers. So for population 1 and population 2, we are looking at the variable x1 and x2. And so then, of course, the sample mean for those would be x1 bar and x2 bar. The mean, of course, is mu1 and mu2, and the standard deviation is sigma 1 and sigma 2. But note that there are 4 unknown parameters, the 2 means and the 2 standard deviations. The subscript reminds us which population a parameter describes. We want to compare the 2 population means either by giving the confidence interval for their difference, mu1 minus mu2, or by testing the hypothesis of no difference, wherein mu1 equals mu2. We use the sample means and standard deviations to estimate the unknown parameters. Again, subscripts remind us which sample a statistic is from. Here is how we describe the samples. So we have populations number 1 and 2, sample sizes n1 and n2, sample means that we get just from calculating the mean of the sample, x1 bar and x2 bar, and of course the standard deviation of the sample, s1 and s2. To do inference about the difference, mu1 minus mu2, between the means of the 2 populations, we start from the difference of x1 bar and x2 bar between the means of the two samples. So we're taking x1 bar minus x2 bar. Let's do an example with daily activity and obesity. First, we state the problem. People gain weight when they take in more energy from food than they expend. James Levine and his collaborators at the Mayo Clinic investigated the link between obesity and energy spent on daily activity. Choose 20 healthy volunteers that don't exercise. Deliberately choose 10 who are lean and 10 who are mildly obese. Attach sensors that monitor the subject's every move for 10 days. And then we have the table here, which I've put in here. This is all the data. Table 17.1 presents data on the time that the subject spent standing or walking, sitting or laying down, and this is in minutes. Do lean or obese people differ in the average that they spend standing and walking? Examine the data and carry out a test of the hypothesis. So here's how we're planning this. We suspect in advance that lean subjects are more active than obese subjects, and so we test the hypothesis. The null hypothesis is that the 2 groups are equal, and again, lean is group 1 and obese is group 2. So this is mu1 and mu2. We're saying that they're equal. That's our null hypothesis. And then our research hypothesis, or the alternative hypothesis, is that mu1 is greater than mu2. So we're choosing this as a one-tailed, so where mu1 is greater than mu2, because we suspect in advance that group 1 is more active. That's how we're setting this up. So group 1 more active than group 2, or mu1 greater than mu2. Here again is the table of all of the data representing minutes in a day. And then here, I should probably get rid of that. And then here is how we calculate N, and notice we have 10 lean ends and 10 obese ends right there. Okay, so here's group 1, which is lean. We have N of 10, and we calculate the mean and the standard deviation. We do the same thing for group 2. The observed difference in mean time per day spent standing or walking is x1 bar minus x2 bar, which is 152. Now notice here that our original our original hypothesis test was that mu1 would be greater than mu2, and so this is kind of lining up with that. But to complete the solve step, we must learn the details of inference comparing two means. So when we have a two-sample situation, there's a slightly different T procedure. Whether an observed difference is surprising depends on the spread of the observations as well as on the two means. Widely different means can arise just by chance if the individual observations vary a great deal. And that's because, again, we're dealing with smaller sample sizes. We're not dealing with whole populations. So to take variation into account, we standardize the observed difference x1 bar minus x2 bar by dividing by its standard deviation. This standard deviation is the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. So I know there's lots of numbers here. This looks complicated, but this is just the sigma of group 1, and we're squaring it. And this is the sigma of group 2, and we square it. So actually, if you remember, this is called the variance, right? If we take sigma squared, that's the variance. So all this is saying is the variance of group 1 and the variance of group 2. But because we don't know this population standard deviations, we don't know those sigmas, we estimate them by the sample standard deviations from our two samples. The result is the standard error, or estimated standard deviation, of the difference in sample means. And so we're just replacing the sigmas with s's there. When we standardize the estimate by dividing by its standard error, the result is the two-sample t-statistic. And the two-sample t-statistic is just the difference in the sample means divided by that standardized standard deviation. Or, excuse me, estimated standard deviation. Okay? The statistic t has the same interpretation as any z or t statistic. It says how far x1 bar minus x2 bar is from 0 in units of standard deviations. There are two options for doing this. Option 1 is with software, which we're not going to be doing in this class. And then option 2 is without software. We use the t-statistic and critical values from the t-distribution with degrees of freedom equal to the smaller of n-1 or n1 minus 1 and n2 minus 1. That's very important. That's how you will be doing this on quizzes and tests. You will look at your two n's and you will take the degrees of freedom, n minus 1, and you'll do that for both population 1 and population 2. And you choose the degrees of freedom equal to the smaller of those two numbers. So if you have one group of 21 data points and the other group of 31 data points, 21 minus 1 is 20 and 31 minus 1 is 30. So you would pick 20 degrees of freedom. You pick the smaller of the two because the smaller number becomes the limiting factor. The smaller is what governs how free your data is to vary. And so we have to use the smaller number because it doesn't overqualify us for preciseness with the resulting distribution. These procedures are always conservative for any two normal populations. The confidence interval has a margin of error as large as or greater than is needed for the desired confidence level. The significance test gives a p-value equal to or greater than the true p-value. Okay? So the two options are exactly the same except for the degrees of freedom used for the t critical values and p-values. As the sample size increase, confidence levels and p-values from option 2 become more accurate. So this is really interesting. The gap between what option 2 reports and the truth is quite small unless the sample sizes are both small and unequal. And for what you'll be doing from me in this class, option 2 is what we're going to be doing. So two sample t procedures. Let's look at this confidence interval. This confidence interval looks more complicated, but it's the exact same structure as we've seen before. So instead of talking about an estimate being a mean, we are now talking about an estimate being a difference of means. So the difference of means is the x1 bar minus x2 bar. That's our estimate. That's our estimate for the parameter. And then it's plus or minus a margin of error. The margin of error is t star, which is that critical t value, and then this adjusted estimated standard deviation. So we're just taking the standard deviation, but we're just adjusting it for like we saw up here. We're adjusting it for the fact that we don't know sigma. We don't know sigma for either population. So here t star is the critical value for confidence level C for the t distribution with degrees of freedom from the smaller of n1 minus 1 and n2 minus 1. To test the hypothesis H0 that mu1 equals mu2, we calculate the two-sample t statistic, and here's what we just saw that on the previous slide, 2 slides ago. Once we've calculated this, a t-value gives us that. A t-value is what bounds us into what we have as an acceptance region, right? And then outside of that, on the top or bottom, outside of that is the the p, that is the rejection region. And so we're interested in comparing the p-value from the t distribution with the smaller, with degrees of freedom of the smaller of n1 minus 1 and n2 minus 1. So here's an example to finish up on that obesity and exercise example. So to solve it, we use inference, of course. The two-sample t statistic for comparing these things is here. And so these numerators are the 525 and the 373 that we got from right here, 525 and 373. And all we're doing here is plugging that in, and then the s's, notice here's S1 and S2, and all of those are just coming from what we calculated as the s's right here. And the s's are then divided by 10 because that's what our sample size was. And we run all of this through here, and we get 3.808. So that's our t-value, okay? So what does this mean? Without software, we use the conservative option 2 because in statistics, being conservative is usually what we want to do, because if we're not conservative, and conservative does not mean anything political, being conservative mathematically means that you're not taking too much liberty in your calculations, and you're not overselling your results for something that they actually might not support. So in statistics, being conservative is the good thing, because it leaves you with results that are realistic and reliable, and that you're not going to have somebody come back to you later and say, the results you gave me are not accurate, because you really were too quote-unquote liberal with the calculation itself. And then the person fell outside of the reliable calculation into this unreliable margin that is created when you're not conservative enough with your math. So without software, we use the conservative option 2, because the n1 minus 1 is 9 and n2 minus 1 is 9. There are 9 degrees of freedom. We don't have to choose the smaller of the two because they're the same size. But because the alternative hypothesis is one-sided, the p-value is the area to the right of that t-value that we just found. So here's what we've got with the t distribution with 9 degrees of freedom. And if we go all the way out to a t of 3.808, that's way out here. Okay, the p-value for that is the area to the right of that. So it is this so small, it is just so small, because it's the t-value of 3.808 is way out there, so it's just this little tiny sliver that you can't even really see. That's our p-value for this. Okay, and then And so because of that, we look in the table C, which is at the back of the textbook, and it shows that this lies, that the t equals 3.808 lies between critical values for 0.0025 and 0.001. So this is how we would say this mathematically. So the p-value is in between 0.001 and 0.0025. It just gives us a range right there. And so note that both of those, if we're doing this for 95% confidence, both of those are smaller than an alpha value of 0.05. So in that case, there is very strong evidence that lean people spend more time walking than do the moderately obese people. So this p is so small that we are rejecting the null hypothesis and going with the alternative hypothesis. I'm not going to make a comment here about robustness, but basically choosing equal sample sizes whenever possible is really preferred. The two-sample t procedures are more robust against non-normality in this case, and the conservative option 2 probability values are most accurate. So it is ideal, if you can, to use to not use software and just calculate it yourself, and then to use equal sample sizes whenever you can. So we're going to do one more example to finish up the video, and we'll keep it under about 40 minutes here. Let's give a 90% confidence interval for mu1 minus mu2. The difference in average daily minutes that these same people are spent standing and walking, the same samples that we had looked at before. So we calculate all this, and notice that we've got this confidence interval here. Our estimate for the target parameter here is again, the target parameter is the difference. So the estimate for the target parameter is the difference here in the x bars. So x bar for 1 and x bar for 2, and then we're plus or minus the t star of 1.833. So if we look in table C under the t distribution for 9 degrees of freedom, and table C is the very last page in your book, and if you open up to the back cover, it literally looks like this, and as you can see, it says table C right here, right? And these are the t critical values. So if we go in here and we look for 9 degrees of freedom, and I just look across, once I have 9 degrees of freedom, which is here, do you see that right there, 9 degrees of freedom, I just look across the page until I find the 90% confidence level, which is 1.833. So if I look under 9 degrees of freedom and I look for the 90% column here, I'm going to get that number of 1.833. Do you see that right there? 1.833. So that's where that 1.833 comes from. And then under the square root, we have the same adjusted standard deviation where we're substituting in the s's because we don't know the population sigmas, and we run all this through and we get our lower limit of 79.09 and our upper limit of 225.87 minutes. And so that is our confidence interval for a two-sample t problem. Thanks so much, guys, and I will see you on Thursday in class.